Hello, and welcome to Boring History for Sleep. Tonight, we will be exploring a subject of profound and quiet ubiquity. Consider for a moment the common light switch plate in a home. In its understated simplicity, it conceals a small, metallic secret, a point of remarkable consistency in a world of constant change. It is held fast to the wall by one or two small screws. Whether that home was built in 1948, 1972, or 1989, whether the plate is beige plastic or polished brass, the screws are almost certainly interchangeable. An electrician from the mid-20th century could likely service a wall outlet installed 3 decades later using the very same screws from his kit. This tiny piece of hardware, the 6-32 oval head machine screw, became an unsung hero of industrial consensus. But how did this seemingly mundane object achieve such an extraordinary level of uniformity across an entire continent and through generations of technological evolution? To truly understand its significance, we must turn back the clock and examine its origins in the chaotic dawn of residential electricity. The journey into the standardization of the electrical device plate screw begins, as many such journeys do, in a state of near-total disarray. At the turn of the 20th century, the American home was a battleground of technologies. The gentle, flickering glow of gaslight, a fixture of domestic life for decades, was being challenged by the steady, brilliant glare of the incandescent electric lamp. This was not a simple transition. It was a fundamental rewiring of the American domestic landscape. Electricity was a force of immense promise, but it was also novel, mysterious, and without proper management, dangerous. The companies at the forefront of this revolution, giants like General Electric and Westinghouse, and a host of smaller but innovative firms like Bryant Electric, Parsons Seymour, and Harvey Hubbell's burgeoning enterprise, were engaged in a fierce competition not just for market share, but for defining the very infrastructure of this new electrical age. In these early years, from roughly 1900 to the early 1920s, there was no central authority dictating the form and function of electrical components. There was no cohesive national electrical code as we would recognize it today, and organizations that would later become the arbiters of standards were either in their infancy or did not yet exist. Each manufacturer was, in essence, its own kingdom, with its own proprietary designs, dimensions, and engineering philosophies. This created an ecosystem of profound incompatibility. An outlet manufactured by one company would not fit into the wall box of another. A light switch from a second firm would require its own specific mounting hardware, completely alien to that of a third. For the nascent profession of the electrician, this was a daily source of frustration and inefficiency. A job site was a veritable museum of mismatched parts. The heart of the problem lay in the components themselves. The system we now take for granted, a standardized metal or plastic box set into the wall, a device like a switch or receptacle screwed into that box, and a decorative plate screwed onto the device, was still in its experimental phase. Early wiring methods, most notably knob and tube, involved running individual insulated copper wires through the voids of walls and ceilings, supported by porcelain knobs and protected by porcelain tubes where they passed through wooden joists. Where a switch or outlet was desired, a box of some kind was needed. These early outlet boxes were a diverse and often crude lot. Some were made of porcelain or soapstone, heavy and brittle materials that could easily crack if a screw was over-tightened. Others were fashioned from folded and soldered sheet metal, often with little thought given to consistent dimensions. Into this inconsistent environment, the device mounting screw was born. It was not a single, identifiable object, but rather a chaotic family of fasteners. Each manufacturer had its own ideas about the ideal way to secure a switch or a receptacle. One company might use a screw with a coarse thread, another a fine thread. The diameter of the screws could vary by fractions of an inch, just enough to make them incompatible. The length was determined by the specific design of the company's own outlet box and device yoke, the metal strap that formed the frame of the switch or receptacle. Head types were equally varied. While the simple slotted drive was universal, the shape of the head could be round, flat, or pan-headed, with no thought given to how a cover plate might eventually sit atop it. The cover plate itself, was something of an afterthought in the earliest installations. The primary goal was function and a modicum of safety. Early switch and outlet mechanisms were often left exposed or were covered by simple functional plates made of stamped brass, nickel-plated steel, or insulating materials like vulcanized fiber. The screws that held these plates on were an even greater source of variation. They did not attach to the device's yoke as they do today, but often directly to the outlet box itself, or sometimes even to a wooden mounting block behind the lathe and plaster. This meant that the screw holes on the plate, the box, and the mounting surface all had to align, a task made difficult by the lack of any dimensional standards. An electrician in 1910 might arrive at a home to replace a broken light switch, only to find that the new switch, from a different manufacturer, would not physically fit the existing box. Even if it did, the screws supplied with the new switch would likely not match the threaded holes in the old box. He might have to drill and tap new holes, a time-consuming and imprecise process. If he lost one of the small, specialized screws that held the cover plate on, finding a replacement was not a simple matter of visiting a local hardware store. He would have to identify the manufacturer of the original part and procure a screw from them or their specific distributor. More often than not, he would rummage through a personal collection of salvaged screws, hoping to find a close enough match. This lack of interchangeability was a significant brake on the efficiency of electrical installation and repair. It added cost, complexity, and time to every job. The materials of these early screws were also a reflection of the era's technology. Brass was common, prized for its corrosion resistance and ease of machining, but it was also soft and the slots could be easily damaged. Steel screws were stronger, but without effective plating, they were prone to rust, especially in the damp plaster walls of the time. Finishes were often a simple matter of utility, a plain blued finish on steel or the natural color of brass. The notion of painting screw heads to match the color of a cover plate was a distant future refinement. The focus was on making a connection, completing a circuit, and moving on to the next task. This period of chaotic innovation could not last. As electricity became more common, moving from a luxury for the wealthy to a necessity for the growing middle class, the inefficiencies of a non-standardized system became increasingly apparent. The burgeoning electrical industry began to recognize that this fragmentation was hindering its own growth. Manufacturers, electricians, insurers, and the public all had a vested interest in creating a more orderly, predictable, and above all, safer electrical environment. The stage was set for the slow, meticulous process of consensus building that would ultimately give birth to the humble 632 screw we know today. The drive for standardization was not a single event, but a gradual convergence of interests, a quiet revolution happening in committee rooms and engineering departments across the country. The 1920s marked a pivotal turning point in the history of American manufacturing, and by extension, in the story of our small screw. The freewheeling, proprietary nature of the early electrical industry began to give way to a more collaborative and systematic approach. The catalyst for this change was the formation of powerful trade associations and independent testing laboratories. These organizations provided the neutral ground where competing manufacturers could meet, debate, and ultimately agree upon a common set of standards that would benefit the entire industry. Chief among these was the National Electrical Manufacturers Association, or NEMA, founded in 1926 through the merger of several smaller industry groups. NEMA's mission was to promote the competitiveness of the U.S. electrical manufacturing industry by, among other things, developing technical standards. NEMA was not a government body, it was a voluntary association. Its power came from the collective agreement of its members, which included nearly all the major electrical equipment manufacturers of the day. A NEMA standard represented a hard-won consensus, a promise from competitors to build their products to a common set of dimensions and performance criteria. At the same time, Underwriters Laboratories, or UL, which had been founded in 1894, was growing in influence. UL's focus was primarily on safety. As an independent testing organization, it would examine electrical products for fire and shock hazards. A UL listing became a powerful mark of quality and safety, one that insurance companies and eventually municipal building codes would begin to require. For a product to earn a UL listing, it had to meet certain construction and performance standards. This created a powerful incentive for manufacturers to abandon idiosyncratic designs in favor of those that could be proven safe and reliable, which often meant standardized designs. Within the meeting rooms of NEMA and in the testing bays of UL, the conversation about standardizing wiring devices began in earnest. The problem was clear. The lack of interchangeability for boxes, devices, and plates was inefficient and potentially unsafe. The solution was to create a unified system. This was a complex task, as it required agreement on dozens of dimensions. They had to standardize the size of the outlet box, the placement of its mounting holes, the dimensions of the device yoke that would screw into it, and, finally, the specifications for the screws that would hold the whole assembly together. The selection of the device-to-box mounting screw thread was a critical decision. The choice fell upon the 632 size. To understand this designation, we must briefly delve into the world of screw threads. The number 6 refers to the major diameter of the screw, a nominal size in a system of gauges where smaller numbers indicate smaller diameters. The number 32 refers to the thread pitch, specifically 32 threads per inch. This combination, 6 to 32, falls into what is known as the Unified National Fine, or UNF, thread series. The choice of a fine thread was deliberate. The metal tabs, or ears, on the device yoke and the threaded holes in the electrical box were typically stamped from relatively thin sheet steel. A fine thread, with its shallower grooves and greater number of threads per inch, provides more surface area for engagement in thin material, creating a stronger and more vibration-resistant connection compared to a coarser thread of the same diameter. The 6 to 32 size was a perfect compromise. It was small enough to be unobtrusive and easy to work with, yet large enough and strong enough to securely hold a device in place against the repeated stresses of plugging in cords and flipping switches. Simultaneously, the standard for the box itself was coalescing. The distance between the centers of the two threaded holes in a standard single-gang device box was set at 3 and 9/30 inches, or approximately 3.28 inches. This precise dimension ensured that any standard device from any manufacturer adhering to the NEMA standard would align perfectly with the holes in any standard box. The era of mismatched devices and boxes was drawing to a close. With the device-to-box mounting settled, attention turned to the final piece of the puzzle, the cover plate and its mounting screws. This was the part of the assembly visible to the homeowner, so aesthetics played a larger role. The committee members and engineers had to decide how the plate would attach not to the box, but to the device itself. They devised a system where the device yoke would be stamped and tapped with another set of threaded holes, located at the vertical centerline of the device. For these holes, the 6 to 32 thread size was chosen again. This was a decision born of elegant simplicity and manufacturing efficiency. By using the same thread size for both the device-to-box mounting and the plate-to-device mounting, the entire system was simplified. A manufacturer only needed to tool up for one tapping operation on their device yokes. An electrician only needed to be concerned with one type of thread on a job site. This seemingly small decision had a profound impact on streamlining the entire installation process. The next consideration was the screw itself. What form should it take? The head needed to be wide enough to securely hold the cover plate, but not so large as to be visually distracting. It needed to sit neatly on the surface of the plate. The choice was made for an oval head with a countersunk bottom. This design allowed the screw to sit slightly proud of the plate surface, creating a gentle, finished dome, while the angled underside of the head nested neatly into the countersunk hole on the plate. This prevented the plate from shifting and created a clean, professional appearance. A flat head screw would have required perfect countersinking to sit flush and could look messy, while a round or pan head would protrude too much. The oval head was the ideal aesthetic and functional compromise. The drive type was, at this point, not a subject of great debate. The slotted drive was the only viable, mass-produced option. The technology for cold-forming, more complex drives like the Phillips head had not yet been perfected or commercialized. The simple slot was easy to manufacture and familiar to every tradesperson. Finally, the length of the screw had to be standardized. The screw needed to be long enough to pass through the cover plate and securely engage the threaded hole in the device yoke beneath. A length of 1/2 inch was determined to be the optimal standard. This provided enough thread engagement for a secure hold in most common installations. For situations where walls were thicker, due to tile or paneling, manufacturers began to offer the same 6-32 oval head screws in longer lengths, such as 3/4 of an inch or 1 inch, but the 1/2 inch screw became the universal standard, packed in with every new plate. By the end of the 1930s, these NEMA and UL-driven standards had been widely adopted. A quiet and powerful uniformity had settled over the industry. A box from one company, a switch from another, and a plate from a third could now be assembled seamlessly by an electrician using a standard set of 6-32 screws. The materials of the screws had also improved. Steel became the dominant material for its strength and low cost, and new plating techniques using zinc or cadmium provided a durable, corrosion-resistant finish. Manufacturers of plates, which were now commonly made from new plastics like Bakelite, began to offer screws with heads painted to match the color of the plate, typically ivory, brown, or black. This small touch marked a shift from purely functional hardware to a component that was also considered part of the home's decor. The age of standardization had arrived, and the 6-32 oval head slotted machine screw was its small but indispensable ambassador. The period from the end of World War II through the 1970s can be considered the golden age of the standardized electrical device screw. The post-war housing boom saw an unprecedented wave of new construction across the United States. Suburbs bloomed, and with them, the demand for standardized, mass-produced building materials skyrocketed. The quiet work done by NEMA and UL in the preceding decades now paid enormous dividends. The ability to produce millions of identical, interchangeable electrical components was essential to the rapid and efficient construction of new homes. In this era, the 6-32 oval head slotted machine screw, in its 1/2 inch length, reigned supreme. It was an object of absolute, unquestioned uniformity. An electrician could walk into any electrical supply house or hardware store in any city and purchase a box of these screws, confident that they would fit any standard device plate in any standard installation. This level of interchangeability was a testament to the success of the standardization process. It had become so deeply embedded in the industry that it was simply taken for granted. The slotted drive remained the undisputed standard for several practical and cultural reasons. First, its manufacturing process was simple and inexpensive. The single slot could be cut or stamped into the screw head with minimal tooling. In an industry focused on producing vast quantities at low cost, this was a significant advantage. Second, the tool required to drive it, a simple flat-blade screwdriver, was universally available. Every toolbox, and indeed many kitchen drawers, contained a screwdriver that could be used to install or remove a switch plate. This accessibility was a key feature. There was also a subtle craft-like aspect to the slotted screw that appealed to meticulous electricians. It became a mark of professional pride to install all the plate screws with their slots oriented vertically. This small detail, invisible to most homeowners, was a quiet signal of a job done with care and attention. It was a finishing touch that demonstrated a level of craftsmanship. The vertical slot created a clean, orderly visual line, and while it had no functional purpose, it became a widely adopted, if unwritten, rule of the trade. This aesthetic consideration further entrenched the slotted screw as the preferred type for this highly visible application. During this mid-century period, the materials of the cover plates themselves were evolving. Early thermoset plastics like Bakelite and urea formaldehyde gave way to more modern thermoplastics like nylon and polycarbonate in the 1960s and 70s. These new materials were more durable, less brittle, and could be produced in a much wider array of colors. This explosion of color in home decor led to a corresponding diversification in screw finishes. It was no longer just ivory, brown, and white. Manufacturers began to offer plates in shades of harvest gold, avocado green, and a host of other colors popular at the time. With each new plate color came a small batch of 6 to 32 screws, their oval heads carefully painted to match. This process of color matching the screw head became a standard part of the manufacturing process, a small but important detail in creating a cohesive look. Despite the dominance of the slotted screw, a new technology was waiting in the wings: the Phillips head. The Phillips drive system was patented in the 1930s by Henry F. Phillips. It was designed primarily for automated industrial assembly lines, particularly in the automotive and aviation industries. The cross-shaped recess was engineered to work with powered drivers. A key feature of the Phillips design was its tendency to cam out, meaning the driver bit would pop out of the recess if a certain amount of torque was exceeded. This was intentional. It was designed to prevent over-tightening and damage to the workpiece or the fastener by the high-speed pneumatic drivers of the era. However, the very feature that made the Phillips head so useful in a factory setting made it less appealing for the delicate task of installing a cover plate. The risk of the screwdriver camming out and skidding across the surface of a brand new, pristine cover plate was a significant deterrent. A slip of the hand could leave a permanent scratch, marring the finished look of the installation. For this low-torque application, where the screw only needed to be snug, the positive engagement of a slotted screw, when used with the correct size screwdriver, was perfectly adequate and perceived as safer for the surrounding surface. Furthermore, the simple inertia of a massive, established system worked against the adoption of the Phillips screw. Millions of electricians were accustomed to using slotted screwdrivers. The entire supply chain, from screw manufacturers to distributors to local hardware stores, was built around the slotted 632 screw. There was no compelling functional or economic reason to switch. The existing system worked perfectly well. As a result, while the Phillips screw became dominant in many other areas of construction and manufacturing, it made very few inroads into the world of device cover plates during this period. The standard itself, however, did accommodate variations for non-standard situations. The half-inch screw was the default, but the system was flexible. If an electrician was installing an outlet over a thick, tiled backsplash in a kitchen, a standard half-inch screw would be too short. To address this, manufacturers produced and sold the same 6-32 oval head screws in a variety of longer lengths, such as 3/4 inch, 1 inch, 1.5 inches, and even 2 inches. These were readily available from electrical suppliers. They were part of the standard, not an exception to it. They ensured that the uniform system could be adapted to the specific conditions of any installation, preserving the integrity of the standard while providing necessary flexibility. The screw material also remained consistent: steel, typically with a zinc plating for a silver finish, or painted to match the plate. Brass screws were still available for decorative brass or bronze plates, where a solid, matching material was desired for aesthetic reasons. In essence, the mid-20th century was a period of profound stability for the device plate screw. It was a time when the standard was so successful and so universally adopted that it became invisible. The 632 oval-head slotted screw was a constant, a reliable and unchanging component in the rapidly modernizing American home. It was a symbol of a mature industry, one that had moved past the chaotic innovation of its youth and settled into a long and productive period of standardized, efficient mass production. Its quiet, unassuming presence on the walls of millions of homes was a silent testament to the power of a well-designed, universally accepted standard. As the 1970s gave way to the 1980s, the deeply entrenched standard for device plate screws began to face new influences and subtle pressures for change. The core specification, the 632 thread, the oval head shape, and the standard lengths remained unshakable. It was too fundamental, too deeply integrated into the entire ecosystem of electrical device manufacturing and installation to be altered. However, the one area where evolution was possible was in the drive type on the screw's head. After decades of the slotted screw's unchallenged dominance, new practicalities began to push the industry toward a more versatile solution. The primary catalyst for this change was the evolving toolkit of the professional electrician. By the 1970s, the Phillips head screw had become the de facto standard in many other areas of construction. It was used for attaching drywall, assembling cabinetry, and in a wide range of other applications where powered drivers offered a significant speed advantage. Electricians, like all tradespeople, found themselves needing to carry and constantly switch between both flat blade and Phillips head screwdrivers throughout their workday. While changing a coverplate screw was a minor task, the need to use a specific driver for it was a small but persistent inefficiency. In response to this, electrical device manufacturers began to experiment with a new design, the combination head screw. This ingenious design featured a head with both a traditional slot and a Phillips-style cross-recess. An electrician could use either a flat blade or a Phillips screwdriver to install or remove the screw. This offered a new level of convenience and flexibility. If they had a Phillips driver in their hand from a previous task, they no longer needed to switch tools to attach the cover plate. The adoption of the combination drive or combo drive was gradual. It first appeared as a premium feature on certain lines of devices and plates. Manufacturers like Leviton, Hubbell, and Parson Seymour began to pack these new screws with their products. Initially, some traditionalists in the electrical trade were skeptical, viewing them as a compromise that did neither job as well as a dedicated drive type. Some argued that the combo head was more prone to stripping than a pure Phillips or slotted screw. However, the sheer convenience of the design soon won over the majority of users. For this specific, low-torque application, the potential downsides of the combo head were negligible. The screw only needed to be snug, not torqued down with great force, so the risk of stripping was minimal. The overwhelming benefit was the reduction in tool switching time. Over the course of a day, wiring a new house with dozens of switches and outlets, those saved seconds added up. By the mid to late 1980s, the combination head screw had largely supplanted the traditional slotted screw as the standard packed with new devices and plates. The venerable slotted screw, which had reigned for over half a century, was gracefully retired to the status of a replacement part or a choice for restoration projects. It is worth considering why other drive types, which were gaining popularity elsewhere, failed to make an impact in this specific niche. The most notable alternative was the Robertson drive or square drive. Invented by a Canadian, P.L. Robertson, in the early 20th century, the square recess offered superior engagement and resistance to cam-out. It was, in many ways, a technically superior design to both the slot and the Phillips head. The Robertson drive became immensely popular in Canada, where it remains the dominant standard for general construction screws. However, it never gained a significant foothold in the United States for a variety of historical and business reasons, often cited as relating to licensing disputes with Henry Ford in the early automotive industry. For the specific application of device plate screws, its failure in the US market was more a matter of overwhelming inertia. The slotted and Phillips systems were completely entrenched. There was no problem with the existing screws that was significant enough to warrant a wholesale shift in manufacturing, distribution, and tool sets to a third incompatible system. The combo head offered a convenient evolution of the existing system, whereas the Robertson drive would have required a revolution. Another drive type that emerged in the latter part of this period was the Torx, or star drive. Developed in the late 1960s, the Torx system was designed for high-torque applications and automated assembly, offering even better engagement and resistance to stripping than Phillips or Robertson. However, it was complete overkill for a device plate screw. The forces involved in attaching a plastic plate to a wall are minuscule, and the high-torque capabilities of a Torx drive were entirely unnecessary. It remained a specialized drive for automotive, electronics, and industrial uses. While the mainstream standard was evolving towards the combo drive, a separate, parallel development was occurring in the realm of security and tamper resistance. In public and institutional settings like schools, hospitals, transit facilities, and government buildings, there was a need to prevent unauthorized removal of cover plates. This was done to prevent vandalism or dangerous access to live electrical wiring. This need gave rise to a family of tamper-resistant screws. These security screws used unconventional drive types for which the corresponding driver bits were not commonly available to the public. One of the earliest and most common was the spanner head, also known as a snake eye, which featured a flat head with two small drilled holes, requiring a special two-pronged driver. Another type was the one-way screw, which had a slotted head that was specially profiled to allow it to be tightened with a standard flat-blade screwdriver, but which could not be unscrewed because the driver would simply slip out of the slanted recess. Other, more complex systems like pin-in Torx or tri-wing screws also saw use in higher security environments. The existence of these specialized security screws serves to highlight the strength and ubiquity of the mainstream standard. They were a deliberate and necessary deviation from the 632 oval head combo drive screw precisely because the standard screw was so common and so easily removed with common tools. The security screw market was a niche, an exception that proved the rule. For the millions of homes across America, the standard held firm. By 1990, the end of our period of study, the standard for a residential electrical device plate mounting screw in the United States had reached a state of highly refined, stable evolution. The foundational elements established half a century earlier remained unchanged. The 632 thread, the oval head shape for a neat countersunk fit, and the half-inch standard length, with longer versions available for non-standard wall thicknesses. The materials were typically zinc-plated steel, or steel with a color-matched painted head. The only significant change had been the near-universal adoption of the combination slotted Phillips drive, a final nod to the practical convenience of the professional electrician. The journey from the chaos of the early 1900s to the quiet, predictable uniformity of 1990 was complete. The meticulous process of standardization had produced an object so successful, so perfectly suited to its task, that it had become an invisible, yet essential, part of the fabric of the modern American home. The small screw was a testament to the power of collaboration, a product of countless committee meetings, engineering debates, and the slow, steady pressure of practical necessity. It was, and remains, a masterpiece of boring, functional design.